linear correlation coefficient. Our objective: describe the properties of the linear correlation coefficient and calculate the linear correlation coefficient using StatCrunch. So what do we know that's going to come into play in this lesson? Two variables have a linear relationship if, as the value of the explanatory variable increases, the value of the response variable increases. That's a positive linear relationship. Or, as the value of the explanatory variable increases, the value of the response variable decreases. That is a negative linear relationship. All right. If we have a linear relationship, we can measure the strength, how strong or how weak, and we can measure the direction, positive or negative, of the relationship. In other words, we can measure how close the points are to a line of best fit, that's the strength, and whether the line goes up from left to right or down from left to right, that's the direction. And we measure this strength and direction using the linear correlation coefficient. Okay, so the linear correlation coefficient is a number that measures the strength and direction of a linear relationship. Let's take a couple notes about the linear correlation coefficient. The Greek letter rho is what's used to represent a population correlation coefficient. So this is a parameter. The lowercase letter r is used to represent the sample correlation coefficient. So r is a statistic. And there's a formula to calculate the sample linear correlation coefficient. There's also one for the population, but we're not going to go there. We don't need to even see that one. But here's the formula for the sample. Okay, again, R represents the sample. And it is quite a mess, to be honest with you. There's a lot going on here. We're not going to worry about this formula. Okay, there's a lot going on there. We're not going to get into all that. We're simply going to ask StatCrunch to do it for us. Hey, StatCrunch, would you please use this formula to calculate R, the sample correlation coefficient? And the way StatCrunch does that is we go to Stat, Summary Stats, Correlation, and it will calculate the sample correlation coefficient, R. Okay, let's now talk a little bit about some properties of the linear correlation coefficient, and then we'll calculate one in StatCrunch. So we have this letter R, this number R, excuse me. The linear correlation coefficient is always between -1 and 1 inclusive. Okay, mathematically, -1 is less than or equal to R. The sample correlation coefficient is less than or equal to 1. If R is +1, we have a perfect positive linear relation between the two variables. The chances of that happening are almost nil. Okay, but this is perfect positive linear relationship. If R is -1, so if we're at the extremes, we have a perfect negative linear relation between the two variables. And again, in real life, these two things don't happen, but those are the extremes. The closer R is to +1, the stronger the evidence is of a positive association between the two variables. Similarly, the closer R, the sample linear correlation coefficient is to -1, the stronger the evidence is of a negative association between the two variables. If R is in the middle, close to 0, okay, then we have little or no evidence of a linear relation between the two variables. Note, R being close to 0 does not imply no relation, it just implies no linear relation. And so here's a picture of this stuff. Here is your perfect negative relationship. Here is your perfect positive relationship. Your positive ones are between 0 and 1. Your negative ones are between 0 and -1. As you're closer to +1, you have a strong you get into a stronger positive linear relation. As you get closer to -1, you're getting stronger and stronger of a negative relationship. And if you're in the 0 vicinity, basically there's a weak, or if it's exactly 0, there's a weak linear relation. Okay, a couple other points. The linear correlation is a unitless measure of association. So the units of measure for x and y play no role in interpreting R, and it's not resistant. Okay, the linear correlation coefficient is not resistant. What does that mean? It can be affected. An observation that does not follow the pattern can affect the value of the coefficient. In other words, and I have here in bold, outliers can have quite an impact on the correlation coefficient, and we're going to want to keep that in mind, that an outlier that doesn't make sense for the rest of the data can have an impact on that number of the linear correlation coefficient. Here are some samples of kind of strong, positive, negative, and different strengths. So here's our perfect positive. R is equal to 1. I can draw a beautiful line right through all those points. Here's our perfect negative. Okay, here is a strong positive. In this case, they say that R is equal to 0.9. It's closer to let me come down a little bit. The 0.9 here is up very close to 1, so that's a strong positive. This one, it looks like it's got a relationship. It's going up from left to right, but it's not very strong. They're saying with an R of 0.4, they're just saying this is moderate, a moderate positive. The strength is moderate. The direction is positive, up, increasing from left to right. And different statisticians in different books call different things strong, moderate, weak. It's kind of up for grabs sometimes. Here is a strong negative relationship with an R of -0.9. Okay, the negative means it's a negative relationship. The 0.9 means it's strong. It's in the strong region. Here's a moderate negative relationship. As the explanatory variable increases, the response variable decreases. You can kind of see there's a relationship, the linear going down, but it's not overly strong. They're calling it moderate. The negative tells us the direction, down from left to right. The 0.4 tells us the strength, not overly strong. Here's no linear relationship at all. There's no good look of line with that one. And here's no linear relation. This again looks to me like it's a quadratic relation because it forms a parabola, but it's certainly not a linear relation. This one looks like it has nothing can model this, but this one looks like it could be modeled by a curve, but not a line, and that's a subject for another statistics class. Okay, let's take a look at what R values can look like. Another example of taking a look at how these scatter plots can look. This one plots the driver age and the sign legibility distance, how far away you can see a sign. And it makes sense, as we get older, we struggle to see things clearly. So our distance for seeing something decreases for legibility. This is saying we have a negative relationship, and it looks like it's moderate to strong, in there with a -0.8. It's on the stronger side. Okay, here's an introductory course average plotted against the upper course average, and that makes sense. If your average grade in the introductory course is high, you would expect your average grade in the next course to be high as well. So here's a positive relationship. It's a positive R, and it's pretty strong at 0.931. You can use, no matter what, StatCrunch will calculate an R value for you, no matter what, even though it may be way off. So here's an R value of -0.172. This is clearly not a linear relation. This is what StatCrunch came up with. This is actually pretty close to a perfect relationship, but it's not linear because I could draw a nice curve through all that more than likely. And here's another one. It gave me a high R value, but this is clearly not a linear relation. It's actually more of a logarithmic relation. For those of you who have worked with logarithms before, you start out fast and then you decrease over time. But StatCrunch can come up with something and it'll tell you it's a positive, strong linear, even though it's not even linear. So StatCrunch, don't rely on StatCrunch to tell you exactly what's going on unless you look at the graph. Okay, after using the scatter plot to determine if a linear relationship exists, the correlation can be calculated in StatCrunch via summary stats correlation. And we're going to go there. We're going to go there just a second. So we have that data set we saw in a previous video that represents commute time in minutes, quantitative variable, together with the well-being index score, another quantitative variable for each individual. We're going to use StatCrunch to determine the linear correlation coefficient between commute time and your well-being index score. Does a linear relationship exist between the commute time and the well-being index score? If so, describe it. Okay, well, let's go to StatCrunch. Give me a moment to let me get my notes together here. All right, let's go into StatCrunch and get it so it's focused, I hope. Okay, so here's my data. We pulled this up before. It comes from dataset 4_1_27. And we want to, well, let's remind ourselves the scatter plot. So graph, scatter plot. Okay, we select the X variable was the commute time. The Y variable was the well-being score. And we went down and we computed it, and here's our scatter plot. It certainly appears that there is a negative linear relationship, and it looks fairly strong. These points, if I were to put a line here, those points all line up on a line pretty well. Then I'm going to do that in just a minute. I'm going to close this, and now I'm going to compute that linear correlation coefficient. And I go to Stat, Summary Stats, and I'll choose Correlation. Okay, I got to select my columns, and I believe I have to select in my case, you got to select both. They need to know both. If you're going to compare two variables, you need to tell the two variables to compare. So you got to select both. In my case, I put check marks in both, and then we should be good here. If I'm not mistaken, I can press compute. And yes, okay, I get this message, and I'm going to highlight it. And it said, let me see if I can, so it's big enough for you to see the correlation between commute time in minutes and Gallup well-being index score is, there it is, a negative 0.981. We knew it was negative, and it's pretty strong. It's pretty close to -1, negative 0.981. We'll make a note of that, but I want to go back. Okay, so that I just calculated my linear correlation coefficient. I want to go back to that. I want to go back to that graph. So I'm going to go back to that scatter plot graph and kind of show you a bit of what's coming up. Let's go back and make that graph. My X variable was the commute time, my explanatory variable. My Y variable is the Gallup index score. I'm going to come down to here, and it says overlay polynomial order. I'm going to select a degree 1. Okay, the polynomial of the degree 1 is a line. Okay, so that's why I selected polynomial degree 1. That's a line. Okay, and it's already defaulting to line of best fit, which is where we're going to be for a lot of this. So now let's press compute. And there you can see the line of best fit. And again, this is coming up, but you can see that these points are pretty close to that line. That's a pretty good fit line for that set of data. But we're going to make use of this line, and I believe we can, well, I can't, no, I'm not able to do that. Let's figure that out when I get there. But there's our line of, what we'll see, our line of best fit, and that's just giving you a heads up, getting you ready for an upcoming lesson. Let's go back and answer our question from the example. Okay, determine the linear correlation coefficient. We determine it R, which is the sample linear correlation coefficient. was a negative 0. I go to 3 decimal places, 981. Does a linear relationship exist? Yes. Okay, if so, describe it. Well, it's negative because it's a negative out front, and it's pretty close to -1, so it's also strong. Negative and strong. In fact, it's very close to -1, so it's quite strong. So yes. Does a relationship exist? Yes, there does. If so, describe it. It is negative and strong.